Assalamualaikum and hi, this is chapter 5 refrigeration cycle video part 2. In this video I'm going to explain subtopic number 3, ideal vapor compression refrigeration cycle. Ideal vapor compression cycle. Ideal vapor compression refrigeration cycle. So first, I already explained in the previous video that we in the reverse Carnot cycle we have a few impracticality. So to solve this impracticality in Carnot refrigeration cycle, first we 100% vaporize before compression, as you can see in the state 1, which I put in the yellow circle. We completely vaporize it into the saturated vapor line there, and the TS diagram can change into the TS diagram as you can see at the bottom of your left hand side slide. So we completely vaporize the state 1 into the saturated vapor line before it goes into the compressor, and that generate work-ins. Another impracticality is the turbine, as you can see here. So we can change the turbine into the throttling device and change it to throttling device, as you can see in this figure. So this is the turbine here, and we change it into expansion capillary or capillary tubes into the expansion valve here. So this is the main component of the refrigeration. As you can see, start from this, which is state 1, and the output of it is state 2 here, and goes into the condenser coil, and the output is state 3 here, and this is the capillary tube or the expansion valve, and the output of it is state 4, and from state 4 it goes into the evaporator coil, and it goes back into state 1 here. And so here is where the heat is absorbed from the refrigerated space, and this is the where heat is released to the surroundings. Refrigerator main components. So this is the simplified diagram of the refrigerator system with the main components, and now we look into the actual refrigerator. This is the actual refrigerator with all the components. Now we look into the simplified one, which is the side view. So as you can see here, condenser coil, and it start from here, which is this is the state 1, goes into the compressor. Here it is at the saturated vapor liquid vapor region, or exactly at the saturated vapor line, and it goes into the compressor, and the output of it is the state 2 here, and then it goes into the condenser, and the output is state 3 here. When it goes into the compressor, the compression increase the temperature, and it goes into the compression superheated region, and then it release the heat to the surrounding, and the output of it is state 3, and then it goes into the expansion valve here, and the output of it here is state 4, and here the heat absorbed QL. And forgot to mention that here is where QH is released to the surrounding, and then now it goes back into the QL, and heat is absorbed from the refrigerated space, and the output of it is state 1 again at the saturated vapor condition. So this is the main component of the refrigerator. As you can see here, this is the evaporator coil, expansion valve, condenser here, and this is the compressor. So this is all 4 components of the refrigerator. Ideal vapor compression refrigeration cycle process and analysis. So this is a simplified diagram of the refrigeration system, and along with the device, and this is the TS diagram. So as you can see in this TS diagram, we have two constant pressure line here, which is this constant pressure line, and also this another one constant pressure line, and process 4 to 1 happen at constant pressure line, and process 2 to 3 also happen at the constant pressure line. And when we look into the pH diagram here, as you can see, process 2 to 3 and process 4 to 1 happen at the constant pressure. So P here is the pressure. Okay, so now we look into the cycle of the refrigeration cycle. The first process is the isentropic compression, which is process 1 to 2. This is the isentropic. First look at the TS diagram, and this is process 1, and this is a process 2. Okay, so this is the isentropic compression, and in the TS diagram, you see that the S value is constant for process 1 and 2. And now we look into the second process, which is the constant pressure heat rejection process, process 2 to 3. And this is the process 2 to 3 at the TS diagram here, 2 to 3, and we have a QH here, which is the heat rejection process, or heat to the warm environment. And as you can see, look at the pH diagram, we have the process 2 to 3 here, and heat is released to the warm environment, and here is the QH. And as already explained and as said before, that the pressure is constant. Here is the constant pressure. So the pressure at state 2 and state 3 is equal. Okay, now we look into the refrigeration cycle of the state 4 to 3, which is the throttling device expansion. And as you can see in the TS diagram, this is process 3 and to 4 here, and we have this line. And in the pH diagram, it's happened at the straight line here. And from this, we know that value of enthalpy at state 3 and state 4 is equal. And now we look into the next process of the refrigeration cycle, which is the constant pressure heat absorption, process 4 to 1, which is the last process. This is process 4 to 1 here, and we have a QL. Look at the TS diagram, and QL is the heat absorption process. And look at the pH diagram. As you can see, the pressure, it happened at the constant pressure line here. P, pressure 4 and pressure 1 is equal here. And since this process is the steady flow device process, so the energy balance equation is equal in the bracket Q in minus Q out plus in the bracket work in minus work out, and it is equal to enthalpy of the exit minus enthalpy at the inlet, HE minus HI. And looking at the heat transfer analysis, we have a constant pressure heat absorption process, which is the QL, and it is equal to H1 minus H4. And another one is constant pressure heat rejection process, which is process 2 to 3. And QH is equal to H2 minus H3. And now we look into the work, which is work net in, is equal to H2 minus H1. And performance, which is the coefficient of power for refrigerant, is equal to QL divided by work net in, and coefficient of power for heat pump is equal to QH divided by work net in. And for the throttling, H3 is equal to H4, as already said in the end. By looking at the pH diagram, we also know that the H3 and H4 is equal. And this is the analysis of the ideal vapor compression refrigeration cycle. This is the end of part 2 for chapter 5. Thank you for your attention, and hopefully you enjoy my video.